So, z-test versus t-test. Well, this gets confusing, and let me give a scenario, okay, that I see all the time. Here's the scenario. Midterm test question comes in, and here is the question. Some description here, retail chain introduced some self-checkout area. They take a sample of size 36, and there you have a sample mean and standard deviations and so on and so forth. 95% confidence interval you're looking for. So you extract information from here, which is X bar is 48.45, sigma is 12.66, N is 36, and you go doing your business solving the problem. You have this information from there. You find the standard error, which is sigma over square root of N. That you find it, 2.11. 5% alpha, 95% in between area. Z gives you 1.96, or that gives you margin of error 1.96 times 2.11, Z sigma X bar, you get that one. Then you compute the lower bound, which is X bar minus margin of error, Z sigma X bar, and the upper bound, X bar plus margin of error equal to this one. And you have this your distribution picture here, and everything looks good until you get a shock, a 4-pointer shock, which is this one. So what went wrong? Everything seems to be perfect in order. Everything is fine. What went wrong? What went wrong was reading the question correctly. Let's go back to the question now. Here it is. This is the line you have to be careful about. The sample shows an average spending of 48.45 with a standard deviation of 12.66. This standard deviation belongs to the sample or the population. The answer quite clearly here is sample, straight away. Sample, sample. You assumed it to be population, and that's where things went wrong. Now, population standard deviation, normally if you have it, it could be wording like historically the standard deviation was this much, or based on previous records, or it's known to be something vague. Here it very clearly says it came from the sample. So this is the very pay attention, serious attention. Now let's do it again. X bar is fine, N is 36 is fine. This is wrong. What do we have here instead? Sample standard deviation. And that means we're going to have T distribution, not Z. T distribution. So that's the thing that you need to worry about when you have these kind of problems. Now let's start again our solution process. Quick one. Margin of error is right here. Standard error and standard error. When sigma is known, we use sigma X bar. When S is known, we use SX bar. Now here is the catch. We need to know sigma, right? In real life, we do not know sigmas, because how would you know sigma of the population? So we approximate it with this one. Just like we approximate population mean with sample mean, we do the same thing with standard deviations. So here we have sigma, and here we have this one. Okay. So the problem is that this is constant. Population standard deviation will not change because population is fixed, right? However, this will keep changing. I take a sample today, it might be 12.43. I take a sample tomorrow, could be 12.76, could be anything there. So this throws us off. When you're computing our estimate, it throws us off. So normally in real life, what we do is anytime you have some doubts about the actual number, you always go for the larger one or the more conservative one. Let's say from here to airport may take 30 minutes, may take 60 minutes. You plan for 60 minutes, not 30 minutes. You invited people for, let's just say, Super Bowl party. And 5 to 8 people say they may come, right? You plan for 8 people. Similarly here, we plan for a bigger number than we would normally do it. And that number comes from here. Z is 1.96, X bar plus minus 1.96 sigma X bar. That's if you know sigma. But if you do not know sigma, then we do this one, T. and t is always bigger than z. So now you can see here that this interval is bigger than that interval. And you can see here in this picture, the green lines are that one, the blue lines are these ones. So the blue lines will always be past the green lines simply because in our mind, this can keep shifting back and forth. So we just give it more room. In fact, t scores are always bigger than z scores, but they become pretty close to z when sample is large. Why is that? Well, when sample is large, this number and that number becomes kind of pretty much equal, right? If you're a very large sample, then there should be pretty much the same. And because of that, we say, okay, well, now we don't need to give that much extra space. That works out there. But for small sample sizes, it's very critical that we use t. Simply because if you look at the t table, if you see the samples are small, this gets even bigger. In this case, in our case, sample was 36, where 2.03 degrees of freedom will be 35, n minus 1. But if you go suppose sample size of 15, it will be much, much bigger than that number there. Because small sample size means we have more doubts about this number. It changes even more. So this is all there is about this thing here, t versus z. You just have to read the problem carefully and focus on the standard deviation belongs to sample or the proportion. If it belongs to sample, use t, otherwise use z. Now when you do proportion, it's always z. No need to worry about that part. And this is the end of this video. I hope you enjoyed it and make sure you learn it properly because questions are coming on the test. Bye-bye.